This video is about an introduction to proofs. Very important. So yes, that is not a proof. That is somebody's idea of a mathematical joke. But you might have seen this sort of string before. Even though this one's an intentional joke, it actually follows sort of the form of a proof, where we're looking at general things, although 6 is not general, but we're looking at general things and arguing things through a sequence of steps. That part is based on a proof. But let's look up some words and terms which lead us up to understanding what a proof is, because in class we will be dealing with them. The first idea is a proposition. You can see here it's merely a mathematical statement. There's some examples there. An axiom is an important word next. Axiom is a proposition or a statement which is assumed to be true, or sometimes it's called a self-evident truth. It requires no proof. So self-evident or an obvious self-evident truth or an obviously true thing. We have to be careful about what we call axioms. Not everything is obviously accepted as an axiom. That one there is quite a befuddling one. The statement is false. That's called a contradiction. A famous mathematician came up with that one. But an axiom is a self-evident truth. Next one is a conjecture. Is a statement that you believe to be true. It hasn't yet been proven. And on the way through to proof, we need to justify. Okay, so that's all about convincing people. And convincing people in mathematics is very tricky at times. It's usually a challenging thing, but it's a very important thing. It's how a lot of progress has been made. Hence the need for mathematical proof. Maths is one of the very few areas where you can actually prove something. You cannot prove everything using maths, obviously, but maths is one of the few areas where something can be proven, whereas in other disciplines we have arguments or a strong demonstration with supporting evidence, something that is testable and retestable, like in science. However, maths is where you can actually prove things, which is a strong term. A bit more on axioms. As we said before, axiom is a self-evident proof. It's self-evidently true without proof. We'll look at some examples of that, and proofs rely on axioms. They are a very important basis for proofs. Ideas associated with axioms are just down here. Some of these ones are called algebraic axioms. So here's some examples. These are key examples. An axiom, alright, can be broken down into various other ones. Something is equal to itself. Alright, that's obviously true. Things equal to themselves are equal to each other. Things equal to the same thing are equal to each other. We use that all the time in maths, probably without fully realizing it. Okay, and so if something is equal to something else and a third thing is equal to that something else, the first two things are equal to each other. The one you don't have to remember the labels, by the way. Just have to appreciate why these are axioms. We're not after you memorizing these terms. It's not necessary, but do appreciate them. Things can be symmetrically axiomatic, so that would mean that in the case here, if A equals B, then we can say B equals A. We do that all the time when we swap things around on the equal signs when we're showing our working. The transitive axiom, it's a bit like the first one. If A equals B and we know that B equals C, then A equals C. That's an important one. So it follows on from that first notion above. Additive axiom, if A equals B and C equals D, then the first and the third equal the sum of the second and the fourth. If A equals B and C equals D, then the product of the first and the third equals the product of the second and the fourth. So it runs on as an extension of this one and the first one above. Another concept is this idea of generalisation, and immensely important. And people say, "Oh, don't generalise." That might be true about people, but in maths, it's incredibly important. It gives maths its tremendous power that it has. It gives it its efficiency and its usefulness, utility. So being able to generalise is pretty much the way proofs go ahead, because otherwise, if you're not generalising, you're just showing one case. Then, well, someone could say, what about the other case? Then you have to show that case. So we don't do specific cases because you'd be there forever. It might actually be impossible in a lot of cases to show every case. So we generalise. If we can do it in general, we've on our way to proving it. Okay, generalising is important. In fact, that's what some mathematicians do in their whole career, generalising. It's tremendously powerful. Alright, so we're going to get on to how to do a proof in class, but I'd like you to realise that there are three main types of proof, but there are many others as well. We're going to focus on direct proof. That's the first one we're going to do. Then we're going to do a more advanced one called proof by induction, or inductive proof. There's another important one you'll maybe see later on in your studies, perhaps in the next year. Proof by contradiction is another big one done at school level, but these first two here, direct proof and proof by induction, are our focus proofs. Okay, this is important. Steps for a proof. Proofs are formal. You do not cut corners ever with a proof. So what you do, you start with a precise statement of what is to be proven. I'm out to prove ... Okay, what we do in high school usually is use the last one, required to prove, or RTP. So we start our proof with required to prove, or usually we abbreviate that to RTP. Occasionally you might see that one. You don't have to worry about lemma or corollary so much at this level. And then we do the logical steps, and that's when we start those logical steps, we put a little subtitle proof. So our first subtitle will be RTP, the second subtitle will be proof, and then the proof is outlined in a series of steps. Major steps should have explanations or annotations, okay, which helps the reader follow what you're doing, and it can help you justify and reason. And then lastly, a final statement of what has been proven. Okay, therefore left hand side equals right hand side, and at the end you put QED, which is an abbreviation for quod erat demonstratum, which is Latin for I've proven what was required and now the proof is complete. Okay, so that's the third subtitle, well, not really a subtitle, but it's the first marking, because it's not a subtitle, it's right at the end. So RTP, proof, and QED. We're going to do some examples in class.